This talk is about what we have learned building a new data platform at British Gas Connected Homes over the last 1 year, 1.5 years. So British Gas, let me talk a little bit about what British Gas Connected Homes is. So British Gas is a 200-year-old company, so you can imagine it's a big company. And at some point, they decided to create a sort of Internet of Things internal startup structure. And this is what Connected Homes is, and that's what I'm going to talk about. Right now, British Gas is the leader in the UK's Connected Homes market. We compete against people like Google Nest, but we think we are actually much further ahead than them, and we have more than 200,000 connected devices at this point, not to say about connected smart meters and all sorts of devices. So in connected homes, what we do is we pick data from lots of different sources, and then we process them, and we try to do smart things with it. So I'm going to go over all the different sources of data we collect and what we do with them. So the first and most obvious data source we have data from is gas and electricity meters. So this in the picture is a smart gas meter. It wakes up every 30 minutes and it sends us information about the home's gas consumption. We also have information about thermostat temperature. We have we sell a product which we sell with our own brand, which is Hive, and this is a connected thermostat. It's something that lets you control your heating from a mobile application, and from that we collect temperature data. Also, we have another project which is starting, which is about connected boilers, water heaters. We have a set of water heaters that send us information, and the purpose of those is to do proactive maintenance, to know when they're going to break, and to be able to repair them. So also another project which I'm going to talk about is about collection of energy data, but in more real time, every 10 seconds. I'm going to talk about this one as well. And in the next year or this year, we're starting to introduce all sorts of new kinds of devices like motion sensors, window and door sensors, and these kind of things. So these are our sources of data. So with respect to meter data, we have millions of gas and electricity customers. I didn't say exactly how many millions because I didn't want to take it wrong, but I think it's around 11 millions. And we have around 600,000 smart meters. Smart meters are being deployed very aggressively, so the idea is that at some point everyone will have a smart meter. And smart meters send us electricity and gas readings every 30 minutes. So we collect all this information, and what we do with this information is this. This is a web page, an application you can access when you are a British Gas customer. This is an old version, so I think that people who are doing that wouldn't be happy that I'm showing this one. There's a better, newer one. But what this does is we collect aggregated energy information. So what we get is total consumption in a home. We don't know if it is the fridge or the heating or hot water or you're using the PlayStation. We don't know that. But we try to find out. So we use machine learning to try and disaggregate this data. So the way we do that is we try, for example, to detect the fridge. The fridge is something that is easy to detect because it has a regular pattern of cycling on and off. So we go and try to detect these components in your aggregated consumption. And what we do at the end is we show what you can see down there. So it's your top 3 spends in February, for example, has been heating, hot water, and appliances. The way we know that is because we're using machine learning to disaggregate this. Another thing we do is we compare you with people who have similar pattern of consumption and a similar profile of home. So in terms of number of rooms, people living in the place and all that. And with that, we can tell you, for example, that you're spending 30% less than similar people people similar to you. Also, we use this information to, so this is all derived from 30 minutes consumption data, but we have lots of customers who send us information like every month or every 3 months we get a read. So we also want to give you similar information if you have one of these meters, these old meters. So what we do is we use the smart meter information from people similar to you to derive this kind of pattern of consumption. Obviously, it's not as accurate, but it's a way to tell you, okay, this is what we think is your pattern of consumption. If you want to have a better accuracy, then you can you please get a smart meter or send us accept to send us this information. So that's what we do with energy data. Then we have the connected thermostats. This is our latest one, which is very nice. The previous one is a white one, which doesn't look that nice. But the important thing is that this thing is sending us a temperature, and it allows you to control your heating. The way we do that is you can do it with a thermostat, but you can also do it with with a mobile application. It is very successful. People like it a lot because you don't want to leave your heating switch on when you leave your home. So if you remember when you're at work, oh, I left my heating switch on, then you can go and switch it off. But also as you can see, we do other things, like you can set a schedule, you can apply a boost. There's a lot of nice functionalities, and people like it very much. So we're selling a lot of those, and right now we have more than 200,000 connected devices in a matter of 2-3 years. And it's growing very fast. So there really is an interest for this kind of devices in the connected home space, and we are adding more connected devices this year. They're starting to sell motion sensors and door and window opening and closing sensors and these kind of things. Another one I just mentioned is the connected boilers. This is right now in trial, but the purpose of this one, that's a boiler, a water heater, and it has this clipping in the front. This sends lots and lots of information to a backend regarding how the boiler is working. And what this does is what the intention is, we want to be able to tell when this is going to break before it breaks. So it's about proactive maintenance. It's about when everyone, like for example, right now, people start to use heating massively. Well, a percentage of these people are going to switch on their heating, and it's not going to work. That's the physical thing. And then there's a lot of British gas engineers who will have to go and fix all this heating, all these boilers in a very short time. So it would be good if we knew that some of these are like not working, and be able to schedule a repair before this happens. So that's what this project is about. And these devices send a lot of information, like very, very frequently. So if you scale that, it's a massive amount of data that we get. Then there is another one. This is when you get a smart meter in the UK, you get this kind of device in the bottom. It's called an in-home display. The idea is that you can control from your kitchen what is your consumption, and the idea is that it will help you save in spending, because you will be more conscious on how much you're spending. Problem with that is that you play a little bit with it, and personally, when I had one at home, it beeped during the night and things like that, so I ended up sticking it in a drawer. So we thought it could be better to have this also in a mobile application. These devices, they communicate via radio with the meters. They use a protocol called Zigbee. So we created a sort of box which goes connected to your router and does exactly the same thing. It's like an in-home display, but it sends us the information every 10 seconds about electricity consumption, and every 30 minutes about gas consumption. Gas consumption doesn't get that often because on an electricity meter you have lots of electricity, but on a gas meter you don't have any electricity. It has to be battery operated. So you want to save, you want to have a battery that lasts for a long time. So what you do is they wake up every 30 minutes and they send us the consumption. So that's how, as often as we can get gas consumption. The beauty of having it in a mobile application, it can send you alerts about consumption in real time. So you can know if there is an abnormal pattern of consumption in your home in real time in your mobile phone. And that's what we are trying, and I'm going to talk about the architecture of this a little bit later on. So that's the technologies we use. Mainly Cassandra, Spark's quite recent, but I would say it's like already something that we are using. Spark, we use Spark for machine learning a lot, and everything we develop in Scala, in engineering. Then there are data scientists who use different languages, like Python and R, but in data engineering, the main language we use is Scala. We are trying different things. I would say the ones that are more interesting for now that we're investigating is SAMSA. SAMSA is a streaming technology which goes very well with Kafka, although it uses Yarn, and then, which is not something we use. And then there is Mesos, which I'm going to talk about why I think this is going to be important in the future. So that's our engineering process. We have a team of data scientists. They have data in their own computers, and they model. They do data modeling with their algorithms and their subset of local data. So once they are confident that they have something that it can be brought into production, then they give it to us, to the data engineering team, and we have to translate and adapt this to run at scale in production. So usually what we do is we translate this to Scala, and we transform it in a way that it can run on Spark, and it can be partitioned and run on different servers at the same time. That is something that it is done on the local computer of the developers, but then this goes to DevOps. It gets into the hands of the DevOps people because it has to be deployed on our staging environment and on our production environment. So here there are 2 points where we have some problems, right? So the technologies are different. In data science, we use Python and R, and they work with relational databases like MySQL, and they have to use local data sets, whereas in engineering, we use Scala and Cassandra, and we in local we use test data. But then to deploy these kind of things, then we have an environment which is built with Puppet, and it has a limited production data set, and then also another one which is built with Puppet and a full production data set. This happens in our own data center, and also we have some deployments in Amazon. So what happens is that there are 2 points of friction. The first one is when we get this model from the data scientists. They have developed in their own way, so they haven't taken into account how this is going to scale, and languages are different as well, and also they want to work with real data, but they don't have an easy way to access it because we're using Cassandra to store our data, and data modeling in Cassandra is hard, and they don't understand when they need to query things in a specific way with respecting specific keys and all that. So that's a point of friction, or not a point of friction because we work very well together, but it slows us down. And then there is another point of friction, is that we develop something in our environment, but then this has to run on an environment which has been deployed by our DevOps teams, and versions have to be the same, and they cannot be upgraded that quickly, and all that kind of thing. So it limits us. It makes us work in a slower way as well, because maybe we want to try something different, but it won't work in staging or in production. So we don't even try it, and we stick to older technologies, and everything takes longer. So this is where we were when we started, and it took us, for our first algorithms took us like more than 6 months to bring to production. And this was very slow. And we were not happy with this. So we have been working in these two areas on how to improve that. So this is our different, it's the solution we have, we have found and which we're starting to work in to solve the DevOps problem. There is usually DevOps people tend to have a different conception of how to do things as to what we really need. We need some sort of data-oriented DevOps. We work with things which are stateful, not stateless. It's not, we don't deploy like an API that can be teared down and rebuilt every time. We work with data nodes that have data and that you cannot destroy and recreate very easily. What we deploy are jobs, are like Spark jobs or ETL jobs. It's not something, it's something that we need to control in a different way. It's not like something that is configuration. You configure it like an API and it works. And then we think it's better to have like a resource management in the sense that you have boxes that look more or less like the same and you run resources on them, rather than splitting these boxes into different small pieces that really will take care of one specific functionality, like what you do with OpenStack, for example. You decide that one part of your box is going to be an API, and one part of your box is going to be some sort of queue, and one part of and it's inflexible. So really it slows you down. So what we have done is we have worked with our own internal, we have built our own internal DevOps team. We call that Data Ops, and what we do is that the same, we have started to use Ansible, and the idea is that the same Ansible scripts that you use to build your servers, you can use inside a Docker instance and use it for your own testing locally. So, so still that leaves like the data science thing apart, but it makes us that we have decoupled the dependencies between data engineering and data operations. So they build our environments and we throw our jobs, and we work together so that the environments we use for testing are the same as they are used for production. If there is an improvement in our Ansible scripts, it gets also deployed to production, and we use always the same thing. So good things about Ansible and Docker. I really am a bit fanatic about Docker and these kind of things, because it's first of all it makes smoother our transition from development to production. You run things locally with the exact same versions you're going to use in production, and you can be for testing end-to-end environments. It is perfect, and you can do it on your own computer. Then you have blue-green deployment possibilities. So you have an API, for example, and you want to switch onto a new version of the API. If you're running that on top of Docker, it's just a matter of in the same box and redirecting your traffic. And if it doesn't work, you redirect it back. And I think that resource managers like Mesos on top of Docker make it much easier to manage your resources. If you have a spike of something, you just can allocate some part of the resources in a more dynamic way. So going in this direction, we have been able to reduce our time to production to less than 2 months. But we still have the problem of how to bring our data science into this. So this is something we haven't solved yet. And what I'm going to talk about now is what we start to have in mind and how to solve it along the same direction. So ideally, I think what data science should be plug and play. We should have some data scientists coming up with algorithms that we could throw directly to our infrastructure, and they could plug into our data pipelines and work. So there are different promising technologies, like for example, in the latest version of Spark, you have data frames with Python and R, and this is very promising. But really, you talk to a data scientist and you say, okay, you have now these data frames in Spark, and they say, okay, but in the first place, why do I need to use Spark? I model my things in my own computer, and and I don't care about scalability and all that. You're complicating my life a little bit if you insist on me doing this. And also, data scientists prefer to have their data sources in a relational database where they can experiment with different joins and things, and that's not how we have the data. And so we need to find a way to make these data sets available to them in a relational way while we have them in Cassandra. So that's a tough thing we haven't solved yet, but I think what the future will look like is something like that. I think that data engineering should be taking care of setting up the pipelines that will get all this data available, whereas the data scientists should be just having models that we can throw at these pipelines. And then data operation should be taking care of having a uniform set of portable environments in the back. So we're investigating possible solutions. So one of them is we are investigating an automated way to export subsets of this data and making them available to in relational databases. Another interesting thing is Spark SQL Server. So being able to query our Cassandra data with an SQL interface. Obviously, this has to be isolated from the rest of the data because it triggers Spark jobs, but that could be interesting as well. By the way, we are using DataStax Enterprise in many parts of our deployments, so it comes together with Spark and Cassandra. And another idea we have is like being able to generate Docker images with a subset of your data so that they could spin up these images, work with them, and this would be exactly the same thing that would be running in production. And I think the objective should be that in less than 1 month we should be able to deploy a new feature. That's what we are aiming at, and hopefully we'll get there someday. So now I'm going to talk about a use case. To show a little bit what is the architecture of how we do it, right? I showed previously, let me go back. No, that's this one, right? So I'm going to talk about how we have implemented this feature of being able to get alerts in real time about abnormal patterns of electricity consumption or gas consumption on a mobile app. So that is what I'm going to what I'm going to talk about right now. So this is what a pattern of consumption over a month superimposed. That's the time, and it's a whole month superimposed, and it's a normal pattern of consumption of a typical home. You can see in the bottom there is a baseline plus the fridge. That is what the baseline of your home and then the fridge are consuming. So we consider that a low consumption. We want to be able to detect this state. The state is like this home is right now is consuming a low amount of energy, and then there is a state of high consumption. That has something that has to be like much less frequent. It has to be a rare occurrence. So if you see there's a red point, I don't know if it can be seen that there is a red point on the top, but that is what we want to be able to detect. That once a month you get an alert, you've been spending too much electricity, or not too much. I mean, maybe you know what you're doing, but there is it's a bit too much. And for that, data scientists have come up with models that they break this into different probability distributions, and I'm not going to go into that because I don't even understand it. But the thing is that they use these probability functions, and they come up with an algorithm which takes into account what is your pattern of consumption over a month in a sort of batched way, in a sort of offline way, and then in real time we get these updates, and there's sort of a sliding window operation that compares against some thresholds, and when there is this event that happens, it triggers an alert. So that's how it looks like right now. So we have the meters, plenty of them. They are sending their information every 10 seconds to a set of APIs in AWS. These APIs act as producers of a Kafka log queue. There's on this Kafka infrastructure, there's a topic which is meter reads every 10 seconds. We currently have 10 partitions on this topic. Then experimentally, what we are doing is we're running some SAMSA jobs on each one of these partitions because we want to be able to we want to be able to get the consumption every 30 minutes. So our algorithm works every 30 minutes. This works every 10 seconds. And also consumption is not the same as a meter read. Consumption is the difference between your last meter reads. So we need to make this, and we need to keep state. For these kind of things, well, there's a developer in our team who is very much a fan of SAMSA, and he has proposed this, and it looks like it works quite well. It works very well with Kafka. Problems with that is, well, it uses Yarn, which we haven't deployed yet, and so different problems. But it is a very promising technology. We could be doing that with Spark as well, what we're doing with SAMSA right now. And then, so at the output of this, we have a Kafka topic of every 30 minutes consumption of electricity for every of our customers. As you see that, there is, we partition the customers according to what the partitioner is from Kafka. And yeah, so I'm saying also that sometimes we miss reads. So SAMSA does also basic interpolation. If we get like every 10 seconds, and then there's 1 hour without reads because someone has disconnected the device, and then it comes back again, what we do is we interpolate and we emit a series of 30 minutes consumptions, which are estimated. So afterwards, what happens is that we get this into Spark streaming. We use Spark streaming to create a streaming context of these 10 partitions. And this Spark streaming context runs every, I don't know, right now if we run it every 10 seconds, yes. So what we need to do here is a bit more complicated. We have, as I said, we have a sort of baseline kind of thresholds which are calculated in a batch mode using another Spark job, which are stored in Cassandra. So Cassandra has its own partitioning. So when you retrieve that with the Spark Cassandra connector, it keeps the partitioning of the partitions in your Cassandra database. I'm going to talk about the partitions because I think it is very important. I think the partition thing is what makes everything right. If you don't get them right, then you start shuffling and nothing works properly. So we repartition this this RDD only once when we retrieve it, when the job starts, to match the partitions of Spark, of Kafka. So also the RDD that is created from Kafka also respects the partitions from Kafka. So what we do is every 10 seconds we join these two data sets, and then what we have is a data set partition which contains information about your consumption right now and also the thresholds that we have calculated for long-term consumption. So if it's, we want it to be different. If it is summer, there is a pattern of consumption which is different from winter, so this is going to change. So we want this to adapt, but not very quickly. So there is a slow rate of adaptation and a fast one. So what we do is at this point, every 10 seconds, we get the new consumptions. We apply a function, which is the machine learning algorithm, and then we output onto another topic, real-time high usage alerts for those for those consumptions that have exceeded the thresholds. I'm not sure if this is too fast or too much, but so that's how it looks, the whole thing. If you see, there is one important particularity of this, which is that you can stretch it vertically. So to be able to do that, it is very important that you get the partitions right, that you don't do any operations that shuffle data. So that's what we try to do. And I would say that that is not that easy. We're doing these kind of things like for the first time, and we're not finding this obvious. I don't know how things will evolve, but it's still doing all these operations in real time, matching the different data sets in Spark. We have found that this is not very easy to do. As I said, the the Spark Cassandra connector is really very good at keeping the same partition as you have with Cassandra. And as also said, it's important to match the partitions from one and the other, from Cassandra and Kafka. So now I'm going to risk to get you very bored, but that is our main Spark Spark loop. And it is, as I said, we have found that this is complicated because so we get here a static data set from Cassandra, which has our thresholds, as I said. Then we get a D stream from Kafka. And first thing we want to do is we want to keep like a buffer of the last 48 half-hour reads, because we also use your short-term behavior to adapt these thresholds. So to do that with Spark, you need to use something which is called update state by key, which is the way to keep state in Spark. And this forces you to do checkpointing. So as you can see, there is checkpointing. There's this update by state by key. Then comes the operation to join with this data set, which is the long-term thresholds. You have to do that before, not inside the for each loop. It's not totally intuitive, but when you think about this, you say, okay, that's how it should work, but it's not that obvious. And then we apply the algorithm, and we go over each RDD of our stream, and then each partition of our stream, because we want every different worker of our Spark streaming job to be publishing, to be a publisher on a producer for our Kafka high medium high consumption topic. So that's as much detail as we get. I'm not going to go in depth anymore, but thought that maybe this would be interesting for someone. So about data partitioning. To me, that's the key of everything. We have suffered of a lot of problems with partitioning. When we started, we knew nothing about Cassandra, and we started creating like huge millions of rows of partitions and things like that. And as you know, if you do this the developer training yesterday, it's something that they tell. So it's a basic thing. You cannot go over like 100,000 cells on a partition, and in 2.2 maybe you can go to several hundred cells, but it's not going to work. But then it's also a matter of common sense. If you work with chunks of things that are too big, your machine is not going to work. So the idea is that actually partitioning data, you would be able to work with anything. At the keynote, Alice was talking about today about what was a 2002 kind of architecture, and it was a little bit like that, right? It's if you have like MySQL databases and APIs, and you shard your customers into different pieces of infrastructure, you could use anything to make these kind of things work. Problem is that you cannot do things across the whole thing, and it gets much more difficult to maintain. But this kind of partitioning, which would be the left one, which is the old one, would work. And we know examples of companies that use this kind of partitioning, and it can scale to big numbers. On the other hand, when you do like something with like Cassandra, these circles there, the idea was to represent a Cassandra-like kind of database, then you have to manage your partitions at the data level. So to do that, we have found that it is very useful to use a partitioning algorithm which is simple and can be implemented in exactly the same way as in any languages. And that is not that easy. We have found, for example, with Murmur3, that we try to use it with Java, and it gives us different results as in Scala. You try to use it in JavaScript or in Python, it gives you completely different results. So if you have a team of people which are working with different languages, and you partition your data according to some hashing algorithm, it has to be something simple and something that you can implement in any language. So what we're using in our team is well, okay. So before that, I'm going to talk. So two partition things in Cassandra. So when you work with time series data, you usually, for example, what we do is we want to make our algorithm run for 1 month of energy consumption for every customer in the UK. That having data stored in this way in Cassandra is not practical. It makes like huge partitions, and is what we did the first time we tried to do that, and it didn't work at all. So the best practice usually is usually is like you will split this according, for example, to months or to hours or to seconds. But sometimes this becomes not practical. So there's another technique which is well known, and it's taught in the development training that happened yesterday, which is use buckets. And this is very easy. You apply a hashing algorithm to your buckets, and then you have like, it has to be consistent. Every customer, according to their customer ID or meter ID, whatever, always ends up in the same bucket. So along your chain, you know that this person is always found in the same place, and it is consistent. And then when you want to retrieve this data, you just do an in close and put all the buckets you want to retrieve, and you get that data. For that, we use an algorithm which is this one. I'm sorry, but I need to finish because I think I have spoken too long already. And you can look at that afterwards. That's what I think it's a good algorithm for sharding. It's called the multiplicative algorithm, and it is very simple. Here's a JavaScript implementation. There's a JS fiddle which you can test if you want to use. And I'm going to skip the summary because I think I've made my time. So that's it. Thank you very much.
Big round of applause.